last mode we're going to look at that is commonly used is the counter mode encryption. So we have our block cipher here with a key, and in counter mode we don't actually encrypt the ciphertext with the don't actually encrypt the plain text with the block cipher, but what we do is we have a unique nonce, a number used once, and a counter, and we encrypt those values with the key. And since what comes out of the block cipher is undistinguishable from randomness, we just use it like the one-time pad, let's say, and just XOR the plain text into this stream of bytes coming out of the block cipher, and then have the ciphertext. And for every block we encrypt, we increment the counter by 1. So in AES, since it works on blocks of 64 bytes, blocks of 16 bytes, this nonce is 8 byte long and the counter is 8 byte long as well. So one thing I want to mention is that obviously this is just XOR, so if we flip bits in this plain text or in the ciphertext, they flip at the exact same position in the ciphertext or in the plain text, obviously. So decryption works exactly the same. Since we have the same nonce, the same counter, and the same key, we get the same key stream, and if we XOR it on the ciphertext, we get the plain text. So, as I said, if we flip as an attacker a bit here, the exact same bit is flipped in the plain text. Counter mode is a way to turn a block cipher into a stream cipher, as you might have noticed. So, one of the most common vulnerabilities in cryptography in general, I would say, is nonce reuse. So if you ever see in a crypto library a parameter that's called nonce, for example, this essentially means this is a number that can only ever be used once. So these nonces have to be generated randomly and can never repeat. Well, why is that? Well, if we have the same nonce here under this and the same key in the encryption, what would happen is we would have the same key stream. And then if we would get our hands on two ciphertexts, we could just XOR them with each other, and the key streams would eliminate each other, and then we would have the XOR of the two plain texts. Now if we know some parts of the plain text, for example, because we know the protocol, let's say we know that they use HTTP, and obviously the first bytes will be HTTP in this protocol, then we also know the first 4 bytes of the other plain text, since we can just XOR this value here with HTTP. This is one method. The other method is use statistical methods, because as it turns out, most systems and also human language is not very random, and we can use statistical methods to recover plain texts if they are XORed with each other. But we're not going to go into detail of that. Nonce reuse is a very common thing to happen because some cryptographic libraries just leave that up to the developer, and the developer might not know what he has to do with that information that he has to submit a nonce, and reuses it. Sometimes nonces are predictable, which can also be a problem. And an example we will see later in the lecture, next week probably, is that's, for example, how the Sony PlayStation code signing got hacked. There in the ECDSA system, that's a signature system. we will see later, is asymmetric cryptography. They reuse the nonce.